Far below the surface, the ocean becomes something else. Light fades, sound travels farther than sight. Pressure begins to shape everything. Above ships pass, aircraft cross invisible lines in the sky. Below, the seafloor drops away. The Bermuda Triangle spans a broad stretch of the western Atlantic between Miami, Bermuda, and Puerto Rico. It is one of the busiest regions of ocean in the world, but beneath it lies one of the deepest points in the Atlantic Ocean. The Puerto Rico Trench descends more than 27,000 feet. At that depth, pressure reaches around 8 tons per square inch. Sunlight cannot reach it. Navigation today is precise. It was not always so. Before satellites, sailors relied on compasses and estimation. Small errors combined with fast currents and shifting weather could grow quickly across open water. Yet the mystery most people think about does not float on the surface. It rests below. What lies along the slopes of that trench? How much of this ocean floor has truly been mapped in detail? What forces shape what sinks, drifts, or vanishes? And how different is the world beneath the waves from the stories told above them? Tonight, we move downward through layers of water and pressure, following the geography rather than the legend. If you enjoy calm journeys like this, I would appreciate it if you gave this one a like and considered subscribing. It helps more curious minds find their way to this peaceful little corner of the internet. And if you feel like sharing, I'd love to know where you're listening from tonight and what time it is where you are. I always enjoy seeing how far these deep sea explorations travel. So now take a deep breath, let your shoulders relax, and together, let's descend slowly into the depths that shape the stories above. On old nautical charts, the region is traced not with borders but with gestures. 3 points connected by habit rather than decree. One rests near the Florida coast, another beside the island of Bermuda, the third along the curve of Puerto Rico. Lines drawn between them form a loose triangle that exists more in tradition than in law, since no treaty or maritime authority ever sealed its edges. The sea itself offers no visible corners, only a gradual blending of waters, where routes intersect and horizons remain unmarked. Across this open expanse, traffic moves steadily. Cargo vessels follow established corridors that curve with currents and coastlines, while aircraft cross overhead in long arcs, guided by invisible grids of navigation. Seen from above, these paths would resemble threads woven through blue fabric, converging and separating with quiet precision. The region rests between continents and island chains, so movement through it has always been constant, like breath passing in and out. Beneath that steady motion, the seafloor tilts and folds in shapes shaped long before any chart recorded them. To the north and west lie broad continental shelves, shallow terraces that extend from the mainland before slipping into deeper water. To the east and south, island arcs rise from submerged ridges, their peaks forming strings of land that catch clouds and trade winds. Between these structures, the crust of the planet bends downward into the long curve of the Puerto Rico Trench, set slightly north of the island that lends it its name. Its presence is not abrupt but gradual, a slow descent where the seabed lowers mile after mile. These contours are the work of plates that drift with patient force. The North American plate presses against the Caribbean plate along this boundary, their meeting neither violent nor still. One edge slides beneath the other, creating a subduction zone where rock sinks into the mantle and the surface above responds with ridges, basins, and scattered tremors. Over ages beyond counting, this motion has sculpted the entire region, arranging its shelves, lifting its islands, and hollowing its deepest floor. Water flows over all of it without pause, softening every outline. Mariners who cross these coordinates rarely sense the architecture below, yet their courses trace its influence. Shipping lanes bend where depths change, flight paths align with weather shaped by the warm sea. The triangle drawn on maps remains an outline of convenience, a storyteller's frame laid across a landscape that answers only to geology and time. Warmth arrives before it is seen. Within the vast Atlantic, a broad current carries water the color of deep sapphire, yet holding the stored heat of equatorial sun. This flowing body is known as the Gulf Stream, a river within the ocean that keeps its own direction and tempo while the surrounding sea drifts more slowly. It begins far to the south, where tropical waters gather energy, then sweeps northward along the curve of North America before bending east toward distant continents, tracing a path shaped by Earth's rotation and the contours of the basin. Its motion is steady and swift compared with the waters around it. In certain stretches, the current can move faster than a person can walk, several miles in a single hour, sliding past the seafloor with quiet determination. Mariners who cross it sometimes notice the boundary without instruments, since the surface can change texture and color where warm flow meets cooler surroundings. The difference is not a line, but a gradual blending, like silk threads merging until they become one fabric. Air above responds to this traveling warmth. As heat rises from the current into the lower atmosphere, it feeds the formation of clouds and influences the paths of winds. Storm systems that pass overhead often draw strength from these waters, gathering moisture that later falls as rain, far from where it first lifted skyward. Along distant shores, climates remain milder than latitude alone would allow, since the current releases its stored warmth into passing air that continues on toward northern lands. Anything floating within this moving stream rarely lingers. Fragments of driftwood, stray nets, and objects lost from decks are carried along its corridor and dispersed across wide distances. The current does not hold them in place, but guides them onward, sometimes drawing them into spiraling eddies that spin like slow wheels before letting them slip away again. In time, such fragments become scattered so widely that their point of origin fades into uncertainty. This great flow is part of a planetary circulation that links oceans together. After turning eastward, its waters cool and sink in far northern latitudes, then begin a gradual return at depth, completing a cycle that may take centuries. Through this vast exchange, heat is redistributed across the globe, softening extremes and shaping patterns of climate that touch coastlines an ocean away. The movement never truly stops. It continues through seasons and centuries alike, a persistent pulse within the Atlantic, carrying warmth, motion, and quiet influence through the dark and open sea. The first sign is often a slow thickening of air, as if the sky itself has begun to breathe more deeply. High above the open Atlantic, faint clusters of clouds gather and dissolve again, until one cluster lingers. Beneath it, the sea holds quiet reservoirs of heat accumulated through long days of sunlight. These warm surface waters release moisture into the atmosphere, and that invisible vapor becomes the seed of towering cloud columns that rise like pale mountains into the upper sky. In this region, the surface temperature often rests above 26 degrees Celsius, a threshold that allows storms to grow with unusual ease. Warm water feeds them continuously, supplying energy through evaporation that condenses into clouds and rain. As air spirals inward toward a forming center of low pressure, Earth's rotation guides the motion into a slow-turning wheel. What begins as scattered thunderstorms can organize into a single rotating system, drawing strength from the sea as long as it remains above those warm layers. Sometimes this strengthening unfolds gradually, Yet at other times, it happens with startling speed. When upper winds remain gentle and the ocean below stays uniformly warm, the structure of a storm can tighten within hours. Pressure falls, winds gather, and the once loose ring of clouds becomes a dense vortex. Meteorologists call this rapid intensification, a process studied closely, yet never entirely predictable, since it depends on delicate balances between air, water, and heat. Even outside fully formed hurricanes, the atmosphere here can shift quickly. Brief squalls appear as compact bursts of wind and rain, descending from darkened patches of cloud that pass almost as soon as they arrive. Within them, downdrafts may rush toward the surface, spreading outward in sudden gusts known as microbursts. These concentrated currents disturb the sea below in fleeting patterns, dimpling the surface before smoothing again, leaving only widening ripples to mark their passing. Storms born in these latitudes follow no fixed schedule. Some curve harmlessly back into open ocean, while others wander along winding paths shaped by distant pressure systems. Subtle changes in temperature or wind direction can alter their course, guiding them across wide arcs of water. Satellites and instruments now watch their movements with patient attention, yet each system retains its own character, shaped by conditions that shift hour by hour above the restless Atlantic. So the sky and sea remain partners in a quiet exchange of heat and motion, their conversation written in cloud spirals and passing rain. From this interplay arise the tempests that have traveled these waters for centuries, forming, turning, and fading according to rhythms older than memory, sustained by warmth drawn gently from the surface below. Long before satellites traced their quiet paths overhead, direction at sea depended on patient observation and steady hands. Mariners once stood beside wooden helms beneath open sky, reading the world through subtle signs. The sun's arc marked east and west, stars revealed north during clear nights, and the swell of waves hinted at distant winds beyond the horizon. These guides formed a language learned slowly, spoken through memory rather than instruments. Among the tools carried across those waters, the magnetic compass held a special place. Its needle, balanced on a fine pivot, aligned itself with Earth's magnetic field and offered a constant point of reference, even when clouds covered every star. Yet that invisible force did not point exactly toward the geographic pole. The difference, known as variation, shifted gradually across the globe, changing from place to place like an unseen tide. Sailors who did not account for it could follow a bearing with complete confidence and still drift miles from their intended course. The compass itself could add another quiet complication. Iron nails, cannon, or cargo stored nearby sometimes influenced the needle, drawing it slightly away from its true direction. This effect, called deviation, required careful correction. Navigators compared compass readings with celestial observations, then adjusted their charts with small, handwritten notes. Such corrections demanded both mathematics and trust in one's own calculations, since the sea offered no fixed markers to confirm the numbers. Dead reckoning filled the long hours between sightings of sun or stars. A ship's speed was estimated with a log line and sand glass, its direction noted again and again, each entry recorded in ink on paper that smelled faintly of salt. Over time, small uncertainties could gather quietly. A current unnoticed beneath the hull, or a wind that pressed the sails at an angle, might nudge the vessel aside, and these gentle deviations, multiplied across days, sometimes placed a crew far from where they believed themselves to be. Within that uncertainty, the human mind played its own role. Distance without landmarks can soften a sense of scale, and repetition of waves may blur the passage of time. A navigator might stare at the horizon until it seemed to tilt or waver, while calculations repeated under lantern light could begin to feel less certain with each review. Confidence and doubt often shared the same narrow chart table, companions through long crossings where confirmation was rare. Gradually, knowledge improved. Tables of magnetic variation were refined, instruments became more precise, and methods passed from one generation of sailors to the next, like heirlooms of thought. Still, those earlier voyages remain part of the ocean's story, reminders of an era when direction was something assembled, piece by piece from sky, instrument, and intuition. Each voyage, a quiet act of interpretation upon an unmarked sea. Color is the first companion to slip away. Just beneath the rolling surface, reds soften into rust, then into muted brown, until they vanish entirely. Oranges follow, then yellows, each hue surrendering to blue as depth increases. This quiet subtraction happens because water absorbs longer wavelengths of light before shorter ones, a gentle filtering that turns the descending world into a narrowing spectrum. Divers who carry bright fabrics downward watch them change shade in their hands, as though the sea were slowly repainting them. Farther below lies a realm oceanographers call the mesopelagic, though its older name, the twilight zone, lingers like a memory of dusk. Here, illumination is neither day nor night, but a dim blue veil that softens outlines and stretches shadows. Shapes remain visible, yet indistinct, their edges blurred as if seen through thin silk. Fish that inhabit this layer often bear large eyes tuned to faint glimmers, and their bodies glint with silver surfaces that scatter what little light remains. As depth increases, even that subdued glow dissolves. The midnight zone begins where sunlight no longer reaches at all, not as a sudden boundary, but as a gradual surrender. Down there, brightness does not arrive from above. Instead, it appears in brief living sparks produced by organisms themselves, small pulses kindled within drifting forms. The surrounding water holds no color in the usual sense, only a dense clarity that reflects nothing back. Along this descent, another presence gathers, one that cannot be seen. The weight of the ocean presses from every direction, increasing with each meter as more water rests overhead. This pressure rises swiftly because liquid does not compress easily, so every added layer contributes its full mass. At a depth of 10 meters, the force has already doubled compared with the surface. Far deeper, it grows immense, a steady embrace that shapes shells, bones, and tissues into forms suited for such conditions. For the human body, which evolved beneath open air, these depths demand careful protection. Without a reinforced vessel, lungs would shrink under compression and gases dissolved in blood would behave unpredictably. Even a brief descent without equalizing pressure can strain delicate membranes within the ears and sinuses. Submersibles and specialized suits serve as small islands of surface conditions, maintaining familiar balance while the sea presses silently outside. Yet the transition downward remains unhurried, layer yielding to layer with patient continuity. Above, sunlight once danced on waves. Below, color withdrew, outlines softened, and weight gathered its quiet strength. The ocean does not conceal these changes. It reveals them slowly, in stages as gentle as evening settling across a landscape, each depth a new shade in a spectrum that belongs only to the deep. Numbers appear first in the story of this place. Long columns of digits recorded by instruments lowered patiently through miles of water. They mark a depression in Earth's crust where the Atlantic floor descends to more than 27,000 feet, a distance so great that mountain ranges could stand within it and still remain hidden below the surface. This vast hollow is known as the Puerto Rico Trench, a slow curve in the planet's skin resting north of the Caribbean islands, shaped not by a single event, but by motions that unfold across geological ages. The trench exists because immense plates of lithosphere meet here in gradual convergence. The North American plate advances with almost imperceptible motion, pressing toward the Caribbean plate. Where they touch, one edge bends and slips beneath the other, a process called subduction. Rock that once lay exposed to open water is carried downward into hotter layers below, while the surface above responds by sagging into a long arc. Sediments drift down from distant currents and settle along the slope, softening its outline even as the underlying crust continues its descent. This boundary is not silent. Deep beneath the seafloor, stresses accumulate where stone resists bending. When that resistance yields, energy releases in brief pulses that travel outward as seismic waves. Instruments anchored across the region record these tremors as delicate vibrations, many too faint for human senses, yet clear to sensitive receivers. Most pass unnoticed, except by monitoring stations, though they reveal that the crust here remains in motion, adjusting itself grain by grain along the plate margin. Understanding such depths once depended on weighted lines lowered from ships, their lengths measured carefully as they vanished into darkness. Modern surveys rely instead on multi-beam sonar, which sends fans of sound downward and listens for their echoes returning from the bottom. Each returning signal carries a trace of shape and distance, allowing computers to assemble detailed relief maps of ridges, slopes, and valleys. Autonomous underwater vehicles glide above the terrain as well, tracing programmed paths while scanning the ground with acoustic vision. Through these methods, the trench has emerged not as an empty void, but as a textured landscape, its walls carved with terraces and its floor lined with subtle folds. Though hidden far below passing vessels, this deep boundary remains part of the living architecture of the planet. Its formation continues at a pace too slow for any single lifetime to witness, yet steady enough that continents shift and ocean basins evolve. The Puerto Rico Trench rests in that quiet continuum, a long shadow in Earth's crust where stone descends, pressure gathers, and time moves with unhurried persistence. Contours hidden beneath miles of water resemble a landscape, remembered from a dream, familiar in form yet concealed from ordinary sight. Far below passing hulls lies a terrain that stretches in broad expanses and sudden rises, its features arranged with the same complexity found on continents. Where depth is greatest, the ground often opens into abyssal plains, immense fields of sediment that extend outward for hundreds of miles. These plains appear smooth when traced on charts, though their stillness is the result of countless particles settling slowly through the water column, each grain descending until it joins a quiet accumulation that levels the terrain over ages. Across these wide reaches stand isolated elevations that rise like submerged ranges. Seamounts form where molten rock once pressed upward through the crust and cooled in darkness, building cones of basalt layer by layer. Some remain solitary, while others gather in chains that mirror the direction of ancient tectonic movement. Their slopes host shifting currents that brush along the stone, shaping ledges and ridges, and in certain places their peaks approach the upper layers of the ocean without ever breaking through. Between plains and heights, the seafloor sometimes opens into long, winding cuts known as submarine canyons. These channels begin near continental margins and descend gradually, their paths carved by sediment flows that move like slow underwater avalanches. Grains of sand and silt tumble downslope through these passages, guided by gravity and density differences, leaving behind sinuous corridors etched into the crust. Over time, these channels deepen and branch, creating patterns as intricate as river valleys on land. Elsewhere, ancient lava flows spread across the bottom in dark sheets, remnants of volcanic activity that once reshaped the ocean basin. When magma emerged from fissures along spreading ridges, it cooled quickly in the surrounding water, forming rounded structures known as pillow basalts. Layer upon layer accumulated until the surface hardened into a mosaic of overlapping forms. Though now still, these formations record episodes when the crust itself opened and renewed, allowing heat from Earth's interior to shape the ocean floor directly. Taken together, these varied structures reveal a landscape far from uniform. Flat expanses lie beside steep escarpments, gentle slopes beside fractured rock, each feature shaped by a different process, acting over spans of time too long for a single era to contain. Currents drift above them, organisms settle upon them, and sediments continue their patient descent, adding fine detail to an already intricate design. The seafloor remains unseen by most who cross above it, yet it stretches below in vast diversity, a hidden geography whose contours rival any terrain touched by daylight. In certain pockets of the seabed, chemistry arranges itself into quiet architecture. Beneath layers of sediment, water molecules form delicate crystalline cages that trap methane within them, creating a substance known as gas hydrate. Though it resembles compacted snow in texture, it remains stable only where cold temperatures and high pressure meet, conditions common along continental margins and deep slopes. There, these pale deposits rest unseen, locked into the seabed like frost, preserved far from sunlight. Such formations develop gradually as organic material settles and breaks down beneath the surface. Microbes consume this buried matter and release methane as a byproduct, which then migrates upward through tiny pores in the sediment. When it reaches zones of sufficient pressure and chill, the gas becomes encased within those icy lattices. Over centuries, this process can create extensive layers of hydrate, some stretching across wide sections of the ocean floor, each crystal holding molecules of methane in still suspension. At times, subtle shifts disturb this balance. Changes in temperature, pressure, or sediment stability may loosen the structure, allowing methane to escape in streams of rising bubbles. These releases can ripple through the water column, altering density in small regions and stirring nearby particles into motion. Instruments lowered from research vessels have recorded such plumes, slender trails ascending slowly until they dissolve into surrounding water. The disturbances are usually localized and brief, yet they reveal how responsive these deposits are to their environment. Stories have long circulated about vast eruptions of gas capable of unsettling ships or aircraft, yet careful measurements have shown that most known seeps are modest in scale. Scientific surveys using sonar and chemical sensors indicate that methane typically escapes in limited quantities, dispersing quickly once it leaves the seabed. While the imagery of sudden, ocean-wide bursts persists in popular imagination, direct observations favor quieter interpretations, grounded in data gathered through repeated expeditions. Even so, these hidden reservoirs hold significance beyond their immediate surroundings. Methane is a potent greenhouse gas, and the hydrates beneath the ocean store immense amounts of it, far exceeding what drifts freely in the atmosphere. Researchers study them closely to understand how shifts in ocean temperature might influence their stability over long spans of time. If warming waters were to reach layers where hydrates lie, some of that stored methane could gradually enter circulation, linking deep geological processes with patterns of climate at the surface. Thus, the seabed shelters both archive and potential, preserving carbon from ancient life while responding to present conditions. Within its sediments, fragile crystals cradle invisible gas, steady for now beneath the weight of the sea. At irregular intervals along the ocean floor, gravity resumes a task it never truly abandons. Slopes that appear settled can hold layers of sediment balanced with delicate precision, each grain resting against another in quiet tension. These deposits accumulate over long spans as particles descend from above or drift sideways from distant sources, forming blankets of silt and clay that thicken slowly along continental margins and submerged ridges. Though they seem still, their stability depends on subtle conditions within the layers themselves. When those conditions change, motion begins without sound. A slight tremor, the steady loading of new sediment, or the gradual buildup of pore water pressure can weaken the bonds between grains. As resistance diminishes, entire sections of seafloor may loosen and slide downslope in a dense flowing mass. This movement resembles an avalanche, yet it unfolds in darkness beneath miles of water, the sediment rolling forward in a clouded surge that reshapes the terrain as it travels. Channels may deepen, ridges may soften, and fresh surfaces appear where older layers once rested. Modern instruments have revealed these events with increasing clarity. Multi-beam sonar sweeps have traced broad scars etched into underwater slopes, their outlines stretching for miles like brushstrokes across the seabed. In some places, long tongues of displaced material extend outward from these scars, showing where sediment once cascaded and settled again. Core samples drawn from such deposits contain jumbled fragments of shells, minerals, and microfossils, evidence of sudden transport rather than gradual settling. Through these observations, scientists reconstruct episodes that occurred long before any witness could have seen them. Occasionally, a large submarine slide can disturb the overlying water enough to send waves outward across the surface. When vast volumes of sediment shift rapidly, they displace surrounding seawater, transferring energy upward. This disturbance may travel great distances as a series of low swells, barely noticeable in open ocean, yet capable of rising higher upon reaching shallow coasts. Geological records along certain shorelines preserve traces of such events, where unusual sand layers lie above older soils, hinting at ancient surges that arrived from far offshore. These processes belong to a history written gradually across the Atlantic basin. Since the ocean first opened, as continents drifted apart, sediments have gathered along its edges, sometimes resting undisturbed for ages, sometimes slipping in sudden descent. Each slide alters the contours below, contributing to a landscape that is never entirely fixed. Over millions of years, this cycle of accumulation and collapse has shaped slopes, plains, and channels alike, arranging the hidden architecture of the seabed through patient repetition. Thus, the ground beneath the water remains quietly active, adjusting its form grain by grain, movement by movement, guided by gravity and time. Not all nourishment begins with light. In the deep ocean, far below the reach of day, entire communities persist where no sunbeam has ever touched the water. Their existence rests on a different source of energy, one drawn from the chemistry of Earth itself. Instead of capturing sunlight, certain microorganisms use reactions between dissolved minerals and compounds rising from the crust. Through this process, known as chemosynthesis, they transform inorganic substances into organic matter, building the foundation of a food web sustained entirely by chemical exchange. These bacteria gather most densely around hydrothermal vents, openings in the seafloor where heated fluid emerges from within the planet. The water that flows out carries dissolved metals and sulfur compounds, creating shimmering plumes that drift into the surrounding darkness. Though the fluid can be hot enough to damage most forms of life, specialized microbes thrive along the edges where temperatures mix and soften. They form pale films across rocks and sediments, quietly converting vent chemicals into nourishment that other organisms can share. Around these microbial colonies, unusual creatures assemble in patient clusters. Tube worms anchor themselves to mineral surfaces, their long white bodies protected within slender sheaths, while crimson plumes extend outward to absorb dissolved substances. They possess no mouths or digestive tracts in the familiar sense. Instead, symbiotic bacteria living inside their tissues perform the chemical work, producing nutrients that sustain both partners. Nearby, translucent shrimp drift in slow arcs, and small crabs move carefully across the uneven ground, each species adapted to conditions that would seem inhospitable elsewhere. Life here depends on balance rather than abundance. Vent flows may fluctuate, shifting slightly over time as subterranean channels open or close. When a vent becomes less active, nearby organisms adjust or disperse, while new colonies sometimes appear where fresh mineral streams emerge. The ecosystem changes gradually, guided by geological forces beneath the crust. In this way, the rhythm of the planet's interior becomes the rhythm of the living community above it. Such environments reveal that photosynthesis, though widespread near the surface, is not the only path by which life can persist. Chemical energy stored in Earth's materials can also support complex systems, allowing organisms to flourish in places once thought barren. Scientists who study these habitats often compare them to early conditions on the young planet, when sunlight struggled to penetrate thick atmospheres and chemical reactions may have played a larger role in sustaining primitive life. Down in these hidden provinces, existence continues through partnerships between mineral and microbe, rock and organism. Nourishment flows from stone rather than sky, and living forms respond with shapes and strategies shaped by their unusual surroundings. The absence of sunlight does not bring emptiness here. It brings a different kind of vitality, one rooted in the quiet alchemy of the deep earth. Light can exist without flame, without heat, without even the sky. In the deep ocean, countless living forms carry their own illumination, small lanterns kindled within their bodies through quiet chemical reactions. Inside specialized cells, molecules such as luciferin meet enzymes called luciferases, and when they combine in the presence of oxygen, energy releases as visible light. The glow is efficient and cool, producing almost no warmth, a trait well suited to waters where excess heat would be wasteful. This living radiance appears in many shades, though blue and green dominate, since those colors travel farthest through seawater. Some creatures emit steady halos, others brief pulses, and a few release drifting clouds of light that linger like luminous mist. The displays are not random. Each pattern serves a purpose shaped by survival, refined through generations that adapted to darkness as their constant surroundings. For hunters, illumination can act as a lure. Certain fish extend delicate filaments tipped with glowing organs, holding them motionless until curious prey approach. The light suggests food or safety, yet when another creature draws near, the waiting mouth closes with swift precision. In other cases, predators use flashes to startle or confuse, creating sudden brightness that disrupts the vision of smaller animals long enough for capture. Prey species have evolved their own uses for radiance. Some produce quick bursts to distract pursuers, while others glow along their undersides in a technique known as counter-illumination. By matching the faint light filtering from above, they soften their silhouettes when seen from below, blending into the dim background. A few release sparkling trails as they swim away, leaving a drifting distraction while they slip into the dark beyond. Across vast stretches of ocean, these signals appear and vanish in quiet succession, forming patterns too scattered for any single observer to follow completely. Tiny plankton flash when disturbed, outlining invisible currents with brief constellations. Transparent jelly forms pulse with rings of light that travel along their edges. Even bacteria contribute, coating drifting particles with a faint sheen that glimmers when stirred. Together, these countless points create a display that extends through immense volumes of water, a dispersed brilliance that surpasses any spectacle on land in sheer scale. The glow does not announce itself loudly. It unfolds in silence, a language spoken through color and rhythm rather than sound. Within that language, communication, camouflage, attraction, and defense all share the same medium, each message carried by a shimmer that lasts only moments before fading. Yet new lights appear as others vanish, continuing the cycle without pause, so that the dark ocean remains quietly alive with flicker and glow, a vast and patient illumination sustained by living chemistry. Forms emerge here not by color or brightness, but by outline alone, silhouettes shaped for a realm where energy is scarce and every movement must be measured. In this depth, animals grow slowly and live patiently, their bodies designed for endurance rather than speed. Flesh tends toward softness, bones toward lightness, since heavy structures would demand more nourishment than the environment can easily provide. The water itself presses from all directions, and so these creatures carry little empty space within them, their tissues balanced to match the surrounding weight. Among the inhabitants drifts the anglerfish, its rounded form scarcely stirring the water as it waits. From its head extends a slender filament tipped with a faint glow, a living lure that sways gently. The fish does not chase. Instead, it relies on stillness, conserving strength while smaller animals approach the light. When they draw close, its jaws open with sudden precision, and the moment of motion ends as quickly as it began. Such efficiency reflects a world where wasted effort cannot easily be replaced. Nearby, gulper eels move with a different design. Their bodies are long and flexible, tapering to thin tails, and their mouths can expand to remarkable size. Rather than hunting a single prey at a time, they open these wide jaws to engulf whatever drifts within reach, water and all. The excess liquid escapes through their gills, leaving behind any edible life caught inside. This method suits an environment where encounters with food are unpredictable, and opportunity must be taken whole when it arrives. Resting along the seafloor are giant isopods, relatives of small crustaceans found in shallower places. Here, they grow far larger, their segmented shells forming protective armor that curves around them like overlapping plates. They move little, often remaining still for long intervals, sustained by a metabolism tuned to scarcity. When nourishment appears, perhaps the remains of a fallen animal drifting down from above, they feed thoroughly and then return to quiet waiting, able to endure long periods without another meal. Pressure shapes every aspect of their existence. Proteins within their cells possess structures that remain stable under immense force, and membranes contain specialized molecules that keep them flexible rather than rigid. Enzymes function at a pace suited to cold surroundings, guiding chemical reactions that unfold slowly but reliably. Even their senses adapt, with organs attuned to faint vibrations or subtle traces of scent carried through the water. Life here proceeds without haste. Movements are deliberate, growth gradual, and cycles extended across years. In this still domain, survival belongs not to the swift, but to the patient, to those whose bodies align with the steady conditions around them. The midnight zone holds these beings in its vast quiet, where endurance becomes the most valuable trait and time itself seems to flow more gently than anywhere above. Long after light has faded from the sea, vibration continues its quiet journey. Water carries sound with remarkable efficiency, allowing waves of pressure to travel far greater distances than they can through air. This happens because the molecules in liquid rest closer together, passing motion along like a steady relay. A single tone released into the depths may glide for miles before losing strength, its energy slipping through the water with patient persistence. Many inhabitants rely on this property as their primary link to the world beyond immediate sight. Whales, among the largest travelers of the ocean, send calls that unfold slowly and resonate across vast ranges. Their voices often fall within low frequencies, which move especially well through dense water. One animal may release a sequence of tones, and another, far beyond any visible horizon, receives it as a distant yet recognizable signal. In this way, individuals remain connected across expanses that would otherwise separate them completely. The ocean itself contains a natural corridor that helps such sounds endure. At certain depths, variations in temperature and pressure create layers where sound waves bend rather than scatter. This region, known to researchers as the SOFAR channel, acts like an acoustic pathway. Tones entering it can become trapped between layers above and below, traveling horizontally with little loss of strength. Instruments placed within this band have recorded calls originating thousands of miles away, their faint patterns preserved by the channel's guiding effect. Not all underwater sound comes from living voices. The shifting of Earth's crust releases low rumbles that drift outward from distant ridges and faults. Ice calving in polar regions sends sharp reports through the sea, and storms imprint rhythmic pulses that descend from the surface into deeper layers. Even rain can be heard below, its droplets striking water with countless tiny impacts that merge into a soft, steady hiss. Human activity adds its own notes to this vast composition. Ships moving across open water produce continuous vibrations from engines and propellers, spreading low frequencies that travel far from their source. Sonar systems emit focused bursts designed to map or navigate, while construction near coasts introduces intermittent pulses that echo through surrounding depths. These additions mingle with natural sounds, forming an ever-changing acoustic landscape that stretches across basins and continental margins alike. Within this layered world of vibration, distance becomes less of a barrier than it appears. Messages, movements, and events announce themselves through pressure waves that slip along unseen paths. The deep ocean listens constantly, filled with tones that overlap and fade, a vast resonant chamber where every sound leaves a trace before dissolving into stillness once more. A person standing on open water often notices the absence before anything else, not a sound or a sight, but the lack of interruption. The horizon forms a perfect circle, unbroken and steady, giving no hint of distance or scale. With no trees, buildings, or mountains to measure against, the eye finds little to anchor itself. Space seems to stretch outward without markers, and the mind, accustomed to walls and edges, begins to search quietly for boundaries that are not there. This visual simplicity influences perception in subtle ways. On land, objects at varying distances provide constant cues that help the brain judge motion and orientation. At sea, those cues fade, replaced by a single line where water meets sky. Without familiar reference points, direction can feel abstract rather than fixed. A vessel may turn gradually, yet to someone on deck, the shift can seem uncertain, since nothing nearby confirms the change. Even the passage of time may appear softened, marked only by the slow movement of clouds or the angle of light. Psychologists who study isolation note that environments lacking variation can heighten awareness of small sensations. The gentle sway beneath one's feet, the steady rhythm of breathing, the faint rustle of clothing, all become more noticeable when there is little else competing for attention. This heightened focus does not arise from danger, but from the mind adjusting to a setting with few external signals. Thoughts may grow more vivid, memories more detailed, as if the quiet around them allows space for inner landscapes to unfold. Distance itself behaves differently across open water. On land, perspective compresses space through layers of objects, yet across the sea the view remains clear for miles. Ships far away can appear suspended between water and sky, their size difficult to judge. Lights at night may seem closer than they are, shining steadily without background context. The brain, evolved in environments rich with depth cues, must interpret a scene that offers very few. Such conditions can create a sensation often described as vastness awareness, a state in which surroundings feel boundless and continuous. Researchers link this experience to the way human perception relies on contrast and structure. When those elements diminish, attention turns inward, and awareness shifts from the outer world to the flow of one's own thoughts. The sea does not impose this change. It simply presents a setting of remarkable uniformity, and the mind responds in its own manner. Out there, the world holds its shape with patient stillness. Sky arches above, water extends below, and between them stands the observer, surrounded by an expanse that offers no immediate landmarks. The quiet persists, not empty but spacious, a broad canvas upon which perception redraws itself, adjusting gently to the scale of the open horizon. Records from early March 1918 describe a vessel moving steadily northward through Atlantic waters, its course plotted in careful ink across naval logs. The ship was the USS Cyclops, a United States Navy cargo carrier built for strength rather than speed, measuring more than 500 feet in length and designed to transport heavy loads across long distances. Its steel hull held vast storage compartments, and during that final voyage, those compartments were filled with manganese ore, a dense mineral used in steel production. The weight of that cargo sat deep within the ship's frame, pressing downward as it traveled away from the coast of Brazil toward Baltimore. The Cyclops had already completed several crossings before this journey, its engines steady and its structure considered reliable for its purpose. Yet reports noted that one of its engines had been out of service, leaving the vessel operating at reduced capacity. Such a condition did not prevent movement, though it may have limited maneuverability in challenging conditions. Aboard were more than 300 people, including crew and passengers, their names preserved in naval archives that still list them in careful sequence. Weather observations from the region at that time suggest unsettled conditions. Seasonal storms sometimes formed along the route, carrying strong winds and heavy seas that could strain even well-built ships. Contemporary accounts from nearby vessels spoke of rough waters during those days, though no direct distress signal from the Cyclops was ever received. Its last known communication indicated no immediate emergency, only routine progress along its path. When the ship failed to arrive, search efforts began, yet they revealed no confirmed debris field, no lifeboats, and no verified trace. Naval inquiries reviewed maintenance records, cargo manifests, and weather data, seeking patterns that might explain the disappearance. Among the possibilities considered were structural stress from the unusually heavy load, shifting cargo that could have affected balance, or a sudden encounter with severe seas. Any of these factors, alone or combined, might have compromised stability, especially if waves struck at angles that strained the hull. Historians who study maritime losses often note that ships can vanish without leaving visible remains, particularly when they sink rapidly in deep water. In such cases, wreckage may descend intact and settle beyond reach of ordinary recovery, preserved only in official documents and the memories of those who searched. The story of the Cyclops rests largely within those written records, lines of type that trace its departure, its intended destination, and the silence that followed. Time has not altered those entries. They remain, as they were first recorded, a sequence of facts describing a voyage that began with purpose and ended without clear explanation, carried forward through history by ink, paper, and the quiet endurance of archived words. 5 aircraft lifted from a Florida air station one afternoon in December 1945, their engines rising in unison as they climbed into clear sky. They were part of a routine naval training exercise known as Flight 19, a formation of TBM Avenger torpedo bombers assigned to practice navigation over open water. The plan was simple and familiar to their crews, a triangular route that would lead them east, then north, then back toward the coast. Each pilot carried instruments, charts, and instructions refined through years of wartime aviation experience. Not long after reaching their first waypoint, radio transmissions began to suggest uncertainty. The flight leader reported that his compass appeared unreliable, its reading no longer matching his expectations. Soon other pilots expressed similar concerns, describing instruments that seemed inconsistent. Without a stable directional reference, orientation over the featureless ocean became difficult since there were no landmarks to confirm position. Voices transmitted through static carried fragments of calculation, each message an attempt to reconcile heading with observation. Weather conditions in the region that afternoon were reported as variable. Earlier skies had been calm, yet later accounts described patches of cloud and areas of reduced visibility. As daylight moved toward evening, the angle of the sun lowered, softening contrasts between sea and sky. Such changes could complicate navigation, especially for crews relying on visual cues to support their instruments. Radio logs preserved from the event record instructions exchanged between the aircraft and their base, voices steady yet increasingly uncertain as time passed. When contact was lost, search operations began promptly. Naval authorities dispatched additional planes and ships to scan the expected flight path. Among them was a large patrol aircraft sent to assist in locating the missing formation. During the search, that aircraft also disappeared after an apparent mid-air explosion, an event later attributed to a fuel vapor ignition, a hazard known to occur in that model. Despite extensive efforts over several days, no confirmed wreckage from the training flight was recovered. Modern analysis draws upon preserved transcripts, maintenance records, and meteorological data to reconstruct what likely unfolded. Investigators generally conclude that navigational misinterpretation played a central role. If the lead pilot believed he was positioned differently than he truly was, the group may have flown farther from land while attempting to correct course. As fuel supplies diminished, the planes would have been forced to descend, eventually reaching the water beyond the range of immediate rescue. The account of Flight 19 endures through documentation rather than physical remains. Logbooks, radio transcripts, and official reports form a narrative assembled from careful notation, each line offering a fragment of the final hours. Together, they present a scene shaped by ordinary training procedures, shifting conditions, and the limits of instruments upon which aviators depended, preserved across decades as a quiet record of a mission that continued into distance and did not return. Numbers tell their stories quietly, without flourish or shadow, arranged in columns that reveal patterns only when read with patience. In maritime records, the region long associated with unusual tales appears instead as one of the busiest corridors on Earth. Commercial routes pass through it in steady succession, vessels moving between continents, islands, and ports that depend on constant exchange. When plotted on global charts of ship traffic, the area shows dense pathways similar to those near other major trade arteries, a sign not of isolation, but of frequent passage. With such heavy use comes a simple mathematical truth. The more ships and aircraft that travel a given region, the greater the total number of reported incidents will be, even when the overall risk remains low. Analysts who compare accident rates against traffic volume find that this stretch of ocean aligns closely with worldwide averages. Losses, mechanical failures, and navigational errors occur there at roughly the same proportion seen in other heavily traveled waters. The figures do not rise above expectation when measured against the scale of movement passing through. Insurance records provide another perspective, since underwriters evaluate risk with careful attention to data. Marine insurers track claims across routes and seasons, noting where hazards appear most frequently. Their assessments have not identified this zone as unusually dangerous. Premium rates for vessels crossing it remain comparable to those for similar voyages elsewhere, reflecting calculations grounded in long histories of documented travel. Such evaluations rely not on legend, but on actuarial tables built from decades of observation. Historical compilations of maritime incidents show a similar pattern. Storms, equipment malfunctions, and human misjudgment account for the majority of losses across all oceans, and the cases attributed to this region fit within those familiar categories. When examined individually, many events once grouped together as mysterious reveal ordinary contributing factors, each consistent with known challenges of navigation and weather. Over time, careful review has clarified that these occurrences do not cluster in unusual concentration compared with other routes of equal activity. Perception, however, does not always follow arithmetic. Stories repeated across generations can gather emphasis, especially when they involve vast settings and incomplete information. A handful of dramatic accounts, retold often, may seem larger than a long list of routine journeys completed without incident. The mind tends to remember striking narratives more readily than uneventful passages, giving rare events a prominence that statistics alone would not suggest. When the records are read line by line, a different portrait appears. The traffic is heavy, the incident rate proportionate, the insurance assessment steady. Movement continues day after day, ship after ship, tracing its course across open water. In the language of numbers, the region speaks with calm consistency, its reputation shaped more by storytelling than by measurable risk. Voices carried across decks have long shaped the character of the sea as much as wind or tide. Sailors, passing months far from land, often filled quiet watches with stories, each tale polished in the telling. Spoken words moved from one crew to another, gathering detail the way shells gather layers. In such retellings, ordinary events could grow more vivid, their edges sharpened by memory and imagination until they settled into shared tradition. The ocean has always offered a stage suited to narrative. Its distances conceal causes, and its horizons reveal little of what lies beyond sight. When an unexpected event occurred, Especially in eras before precise instruments, explanations were sometimes built from fragments of observation. A strange light, an uncharted shoal, or a sudden loss of contact might be described first as fact, then as interpretation, and finally as legend. Each retelling smoothed uncertainty into a shape that listeners could hold in their thoughts. Human perception plays a quiet role in this process. The mind is skilled at recognizing patterns, even when information is incomplete. This ability helps people make sense of complex surroundings, yet it can also connect unrelated events into a single thread. When several incidents happen within the same broad region, memory may group them together, giving them a sense of shared meaning. Over time, repetition strengthens the association until the connection feels natural rather than constructed. During the 20th century, new forms of communication allowed such stories to travel far beyond the decks where they began. Newspapers, magazines, and later radio and television found audiences eager for accounts of unusual happenings. Reports that emphasized mystery or suspense often drew more attention than those describing routine voyages. As these accounts circulated, they sometimes highlighted dramatic elements while omitting ordinary context, shaping public perception through selective detail. The result was a narrative that seemed larger than the scattered events from which it arose. This process did not require intention or deception. It unfolded gradually, guided by curiosity and the human preference for stories that stir imagination. Writers quoted earlier reports, readers repeated what they had heard, and the cycle continued, each step reinforcing the last. In time, a reputation could form around a place or occurrence, sustained less by new evidence than by the echo of previous descriptions. Across generations, such myths became part of maritime culture, woven alongside practical knowledge of winds and currents. They served as entertainment, caution, and shared identity all at once. Even now, long after navigation has grown precise and records have become detailed, these narratives endure, carried forward in conversation and print. They drift through history, much like songs remembered from childhood, familiar not because they describe every detail exactly, but because they have been told so often that their presence feels as natural as the sea itself. Traces do not linger long once they enter the sea. Objects that slip beneath the surface begin to change almost at once, their edges softened by water rich in dissolved salts. Metal reacts with this environment through electrochemical processes, forming oxides that flake away in thin layers. Iron becomes lacework, steel loosens grain by grain, and even sturdy alloys yield gradually. The transformation is not dramatic but steady, a quiet wearing down that continues day after day until shapes lose their sharpness and strength. Living communities assist in this slow disappearance. Small scavengers gather wherever new material settles, drawn by scent and vibration. Crustaceans, worms, and microorganisms move across surfaces, feeding on organic remains and leaving only fragments behind. Bacteria colonize exposed areas and produce enzymes that break down tissues invisible to the eye. Over time, these countless tiny actions reduce once solid forms to scattered pieces, each carried or consumed until little recognizable structure remains. Meanwhile, fine particles drift downward through the water, settling gently across the seafloor. This rain of sediment may seem delicate, yet its persistence allows it to blanket objects with surprising efficiency. A lost item can become coated within months or years, its outline softened beneath layers of silt and clay. As deposits thicken, they press lightly from above, tucking the object into the seabed's upper skin. In places where sediment accumulates quickly, Burial may occur long before corrosion or scavengers have finished their work. Movement within the water itself further obscures what once was visible. Currents slide along slopes and across plains, lifting small fragments and carrying them away. A single structure may be separated into many pieces, each drifting in a different direction before settling again. Some fragments travel only a short distance, while others are transported far from their origin, guided by flows that trace paths invisible from above. This dispersal scatters evidence across wide areas, making it difficult to reconstruct a single, clear scene. Time deepens the effect. As years pass, chemical reactions continue, sediments accumulate, and living organisms return again and again to whatever remains. Edges round off, colors fade, and textures blend with the surrounding ground. Even materials designed to endure harsh conditions eventually merge with their environment, their components incorporated into mineral layers or biological cycles. The ocean does not conceal through sudden action. It conceals through persistence, allowing many small processes to overlap until distinction gives way to continuity. In this way, the seafloor becomes both archive and eraser. It receives what descends from above, holds it for a while, then gradually folds it into the larger fabric of its terrain. What once seemed separate becomes part of the landscape itself, indistinguishable from the grains and stones nearby, resting quietly within the long memory of the sea. Before a map exists, there is only depth without outline, distance without contour. To reveal what lies below, researchers send sound instead of light. Multi-beam sonar spreads pulses downward in wide fans, each signal traveling through water until it meets the seafloor and returns as an echo. By measuring how long those echoes take to come back, computers calculate distance with remarkable precision, assembling millions of points into digital terrain. As a vessel moves forward, these measurements accumulate in overlapping swaths, gradually forming a detailed relief that shows slopes, ridges, and basins hidden far beneath. The process unfolds slowly because the area to be measured is vast, and the swath beneath a ship covers only a narrow corridor at a time. Even with advanced equipment, a single expedition may chart only a small fraction of the surrounding basin. Researchers must guide their vessels along carefully planned tracks, ensuring each pass overlaps the last so no gaps remain. The result is a methodical weaving of data, thread by thread, until the pattern of the seafloor begins to emerge. In places too deep or complex for surface ships alone, autonomous underwater vehicles descend to continue the survey. These robotic explorers travel close to the bottom, following programmed routes while scanning their surroundings with sonar and cameras. Because they operate nearer to the terrain, they can capture finer details, revealing textures and formations that broader surveys might miss. After completing their missions, they rise again carrying stored recordings, which scientists later merge with other measurements to refine the growing map. Observation does not rely solely on instruments within the water. Satellites orbiting high above the planet contribute their own perspective through a technique known as altimetry. By measuring slight variations in sea surface height, they detect the subtle gravitational pull of underwater features. A submerged mountain, for instance, exerts a faint attraction on the water above it, creating a gentle bulge that sensitive sensors can detect. From these delicate changes, researchers infer the presence of large structures across regions that ships have not yet surveyed directly. Despite such innovations, charting the ocean floor remains a demanding undertaking. Ships require fuel, crews, and time, while specialized equipment must withstand pressure, corrosion, and long deployments. Weather can delay operations, and remote locations may take weeks to reach. Each dataset must also be processed, corrected, and verified, a task that continues long after the expedition ends. The cost reflects this combination of distance, duration, and precision. Yet, with every survey, the unknown yields a little more of its form. Lines appear where once there were none, contours replace blank space, and the hidden landscape gains clarity. Progress advances patiently, chart by chart, as technology and persistence work together to sketch the vast terrain that rests beneath the waves. Weight gathers quietly in the ocean, not as a sudden force, but as a steady accumulation that builds with every descending meter. Water above presses on water below, and that pressure transfers in all directions at once, surrounding anything that moves beneath the surface. For every 10 meters of depth, the load increases by roughly 1 atmosphere, adding another layer of invisible mass. Far down, this burden becomes immense, a silent presence that shapes every structure and motion within its reach. Human technology must adapt carefully to endure such conditions. Submersibles designed for deep exploration rely on shapes that distribute force evenly, often forming thick, spherical, or cylindrical hulls. Curved surfaces prevent stress from concentrating at corners, allowing the vessel to resist compression from the surrounding sea. Even a small weakness in construction could permit water to push inward with overwhelming strength. So engineers calculate tolerances with extraordinary precision before any descent begins. Materials chosen for these craft must combine strength with resilience. High-grade steel has long been used for its durability, yet modern designs often incorporate titanium alloys, which provide comparable strength with reduced weight and greater resistance to corrosion. Transparent viewports present another challenge, since they must remain clear while withstanding intense force. For this purpose, manufacturers shape acrylic or specialized glass into thick, rounded panes, each tested under simulated pressure before it is ever placed within a hull. Inside these vessels, conditions remain calm despite the immense load outside. Air pressure is maintained at levels comfortable for human occupants, and instruments monitor every detail of the surrounding environment. As a submersible descends, sensors register the rising force pressing against its exterior, numbers increasing steadily on digital displays. The craft itself may creak faintly as its frame adjusts, a natural response of metal settling under strain. Explorers have carried such machines into some of the deepest reaches of the Atlantic. Record-setting dives have reached depths measured in miles, where the pressure outside exceeds thousands of pounds on every square inch. These journeys require meticulous preparation, from calculating buoyancy to planning ascent rates that ensure stability. Each successful descent adds to a growing understanding of how materials behave under extreme conditions and how technology can safely accompany humans into realms once considered unreachable. The ocean does not resist these visits. It simply applies its constant force, the same pressure that shapes rocks, sediments, and living forms alike. Within that steady embrace, submersibles travel as brief guests, protected by careful design and patient engineering, descending through layers of weight that continue to build, silent and unseen. As depth increases, beneath the broad Atlantic, the ground is never entirely still. Far below the drifting layers of water, immense slabs of crust press and slide against one another along boundaries that trace slow lines across the planet. Near these margins, motion unfolds gradually most of the time, yet tension can gather where rock resists bending. When that stored strain releases, the surrounding stone shifts with sudden force, sending vibrations outward through the solid earth and into the water above. These underwater earthquakes occur most often where tectonic plates meet. Along certain edges, one plate moves past another, their surfaces grinding in opposite directions. In other regions, a plate sinks beneath its neighbor, descending toward deeper layers of the mantle. Each type of boundary produces its own pattern of tremors, from gentle adjustments that barely register to stronger jolts that ripple across wide distances. Though hidden from sight, these events contribute quietly to the changing shape of the ocean basin. Networks of instruments listen constantly for such motions. Seismographs anchored on land detect distant quakes through waves that travel through the planet's interior, while specialized sensors placed on the seafloor record vibrations closer to their source. These devices translate movement into lines of data, tracing the strength, depth, and location of each event. Scientists compare these records from many stations at once, allowing them to pinpoint where a tremor began and how its energy spread outward. Over long spans of time, repeated earthquakes help sculpt the sea floor. Fault lines shift slightly with each release of strain, raising some sections and lowering others. Ridges may rise as magma wells upward through fractures, while basins deepen where crust pulls apart or subsides. Sediments slide and settle after each disturbance, smoothing certain areas and reshaping slopes elsewhere. The basin that holds the Atlantic today reflects countless such adjustments, layered across millions of years, each tremor a small contribution to a vast geological design. Occasionally, a quake beneath the ocean floor can influence the water itself. If the seafloor moves abruptly upward or downward, it may displace the column of water above, sending waves outward across the surface. These waves can travel great distances with little loss of energy, spreading from their origin in wide arcs. Regions near active plate boundaries monitor such possibilities closely, maintaining alert systems that analyze seismic signals in real time. Most underwater earthquakes pass without producing significant surface disturbance, yet the potential for larger shifts remains part of the natural rhythm of the planet. Deep below passing ships, these movements continue with patient regularity. Rock bends, releases, and settles again, guided by forces that have shaped Earth since its earliest ages. Though rarely noticed at the surface, the quiet work of these tremors persists, adjusting the architecture of the Atlantic, one subtle motion at a time. Change in the ocean rarely announces itself in a single moment. It unfolds through subtle adjustments, measured not in sudden events, but in averages gathered across years. Instruments lowered from research vessels and sensors anchored to drifting buoys have recorded a gradual rise in water temperature across many parts of the Atlantic. The increase is small when considered day by day, yet over decades it becomes clear. A slow accumulation of heat absorbed from the atmosphere and carried through currents that circulate across the basin. Warmer water influences the energy available to weather systems that pass overhead. Storms that draw strength from the sea can gain additional momentum when surface layers hold more heat, since evaporation supplies moisture that fuels cloud formation. Studies comparing records across time suggest that while the total number of storms does not always increase, the proportion reaching higher intensity has shown measurable change in several regions. This shift reflects the delicate balance between temperature, air movement, and moisture that shapes each system's development. Large currents also respond to these gradual variations, The great stream that flows along the western Atlantic depends partly on contrasts in temperature and salinity between different latitudes. As polar ice melts and rainfall patterns adjust, fresh water enters northern seas, altering density and influencing how water sinks and circulates. Observations indicate that sections of this current have experienced subtle changes in speed and structure. Such variations remain an active area of study, since even modest shifts could influence climate patterns along distant shores. Sea level has likewise shown a steady upward trend. Thermal expansion plays a role, since water occupies slightly more volume as it warms. Added to this is the contribution from melting glaciers and ice sheets, which release stored fresh water into the ocean. Along coastlines bordering the Atlantic, tide gauges and satellite measurements reveal that average levels have risen over the past century, though the amount differs from place to place. Local factors such as land movement and regional currents can amplify or reduce the effect in particular areas. These processes do not operate in isolation. Heat absorbed in one region may travel thousands of miles through moving water, while atmospheric shifts can influence currents far from their origin. Scientists analyze these connections through long-term data sets, computer simulations, and repeated field observations, assembling a picture that grows more detailed with each passing year. The story that emerges is one of interlinked systems adjusting gradually to new conditions. Across the wide Atlantic, the surface may appear unchanged to a passing glance, yet measurements reveal a quiet transformation underway. Temperature, circulation, storm behavior, and shoreline boundaries all respond to the same underlying influence, unfolding slowly across time. Along the margins where continental slopes descend into darker water, delicate structures rise that resemble pale gardens carved from stone. These are deep water coral systems, built not in bright shallows, but in cool depths where sunlight never reaches. Their branches grow slowly, layer upon layer of calcium carbonate, secreted by tiny polyps that extend soft feeding tentacles into passing currents. Unlike tropical reefs, they do not rely on symbiotic algae for nourishment. Instead, they gather drifting particles and microscopic organisms carried along invisible flows, sustaining themselves through patient filtration. Cold water corals thrive where temperatures remain low and nutrients move steadily through the water column. Their forms vary from intricate fans to clustered mounds, each shape influenced by current speed and direction. Because growth occurs so gradually, some colonies may persist for centuries, recording environmental conditions within their layered skeletons. Scientists studying these formations often compare them to living archives, since chemical traces within the coral can reveal past changes in ocean chemistry and temperature. In the waters surrounding Bermuda, such habitats support a remarkable array of life. Fish seek shelter among the branching frameworks. Crustaceans cling to crevices, and soft-bodied organisms settle along shaded surfaces. Sponges and anemones add texture to the scene, forming communities that depend on the coral's structure for stability. Though these ecosystems lie far below the surface, their influence extends upward, providing nursery grounds and feeding areas that contribute to the health of species found in shallower zones. Yet these quiet formations exist in a state of balance that can be altered by distant activity. Fishing gear dragged along the seafloor may break fragile branches that require decades to form. Changes in ocean chemistry, particularly shifts in acidity caused by increased carbon dioxide absorption, can affect the ability of corals to build their skeletons. Even slight variations in temperature or sediment flow may influence how successfully new colonies establish themselves. Because growth is so slow, recovery from disturbance can take many years. Researchers explore these reefs using remotely operated vehicles equipped with cameras and sampling tools, allowing observation without direct contact. The images they capture reveal landscapes of surprising intricacy, where pale coral limbs extend like frost patterns across the dark substrate. Each expedition adds detail to scientific understanding, showing how life adapts to environments once thought too harsh to support such richness. These coral systems persist quietly along the ocean's edge, shaped by currents, chemistry, and time. Their presence reminds observers that diversity does not depend on brightness or warmth alone. In cool depths, near Bermuda and beyond, delicate frameworks continue to grow, sustaining communities that flourish in stillness, far from the surface yet firmly woven into the fabric of the sea. Far below the restless surface, a quiet exchange takes place that links the smallest drifting cells to the vast chemistry of the planet. Near the upper layers of the ocean, microscopic plants absorb carbon dioxide during photosynthesis, weaving it into delicate structures that sustain their growth. When these organisms die or are consumed, fragments of their bodies begin a slow descent. This steady fall of organic material is often called marine snow, a gentle shower of particles that drifts downward through the water column like pale dust settling through still air. As these particles sink, some are eaten along the way, yet a portion continues its journey until it reaches the deep seafloor. There, the carbon once held in living tissue becomes part of the sediment, tucked into layers that may remain undisturbed for centuries or longer. This process forms what scientists describe as the biological pump, a natural system that transfers carbon from the atmosphere and surface waters into long-term storage below. It functions without haste, guided by gravity and the life cycles of countless organisms working in unison. On the broad plains of the abyss, where sediments accumulate grain by grain, this stored carbon rests within the Earth's crust. Over immense spans of time, pressure compacts these deposits, sealing them into the geological record. In this way, the deep ocean acts as a reservoir, holding vast quantities of carbon that might otherwise circulate freely in the air. The effect extends beyond the depths themselves, influencing global climate by regulating how much carbon dioxide remains in the atmosphere. Temperature, currents, and biological activity all shape how efficiently this system operates. If surface waters warm or nutrient supplies shift, the productivity of microscopic plants can change, altering the amount of material that begins the downward journey. Likewise, variations in ocean circulation may affect how long carbon stays stored below before returning to upper layers. Researchers study these patterns through sediment cores, chemical tracers, and long-term monitoring, assembling evidence that reveals how closely ocean processes intertwine with planetary balance. Deep ecosystems play a subtle yet essential role in maintaining this cycle. Organisms living along the seabed help redistribute settling particles, mixing them into sediments and influencing how they are preserved. Burrowing animals stir the upper layers of the ocean floor, while microbes transform organic compounds into forms that can remain stable for extended periods. Each action contributes to a system that depends on cooperation between biology, chemistry, and geology. Within these hidden depths, the ocean performs one of its quietest tasks. Carbon drawn from the air finds its way downward through living pathways and comes to rest in the stillness below, where time stretches far beyond the span of seasons. Maps of the deep ocean still contain more blank space than detail, their shaded contours interrupted by wide stretches where measurements remain sparse. Despite centuries of seafaring and decades of modern research, only a small portion of the global seafloor has been charted in high resolution. Current estimates suggest that less than 1/4 has been mapped with the clarity needed to reveal fine structure. The remaining expanse lies recorded only in broad outlines, its features inferred from distant readings rather than traced directly. This incomplete picture reflects the sheer scale of the ocean basin. Survey vessels must travel slowly while scanning the bottom, and each expedition covers only a narrow corridor at a time. Weather, distance, and equipment limits all influence how much territory can be measured during a single voyage. Even with advanced instruments, progress advances in careful increments, each new dataset filling another slender strip on the chart. Research missions continue throughout the year, dispatched by universities, government agencies, and scientific institutes. Some ships tow arrays of sensors behind them, while others deploy robotic explorers that descend to collect imagery and samples. These expeditions often focus on specific goals, such as studying geological formations, cataloging unfamiliar species, or examining chemical conditions near the seabed. When the vessels return to port, their findings join shared archives where specialists analyze the information and compare it with earlier surveys. Many of these efforts take place through international collaboration. Ocean currents and geological features do not follow political boundaries, so researchers from different nations combine resources to study them. Cooperative programs coordinate mapping campaigns, share satellite data, and establish standards for processing measurements. By pooling expertise and equipment, these partnerships expand the reach of exploration beyond what any single institution could accomplish alone. The deep ocean remains a frontier not because it is unreachable, but because it demands patience. Pressure, darkness, and distance require technology capable of operating reliably under conditions unlike those on land. Instruments must withstand corrosion, vehicles must navigate without direct human guidance, and communication with submerged equipment often depends on slow acoustic signals. Each challenge has prompted new designs, from pressure-resistant housings to navigation systems that rely on sound rather than sight. As these innovations develop, the unknown areas gradually shrink, though they do so at a measured pace. With every expedition, additional ridges, valleys, and plains appear on updated charts, replacing blank sections with precise contours. Yet vast regions still await their first detailed survey, resting quietly beneath the surface. Exploration continues step by step, chart by chart, as scientists and engineers extend their reach into one of Earth's least explored realms, guided by curiosity and the steady accumulation of knowledge. Darkness has a texture the mind can sense even when the eyes cannot. In places where light is absent for long stretches, perception begins to shift, adjusting itself to an environment without familiar signals. Human awareness evolved beneath open skies and shifting daylight, where brightness marked safety and shadow suggested uncertainty. Over many generations, the brain learned to treat darkness as a condition that required attention, since limited visibility once meant hidden terrain, unseen movement, or the approach of night when ancient travelers sought shelter. Without light, the visual system has little to anchor itself. Depth becomes uncertain, distance loses meaning, and outlines dissolve into a uniform field. The horizon, that quiet reference line that usually steadies orientation, disappears entirely. In such surroundings, the mind searches for patterns, sometimes creating faint impressions where none exist, as though it prefers imagined structure to complete absence. This tendency reflects the way neural circuits interpret incomplete information, filling gaps so perception feels continuous. Time also behaves differently in prolonged darkness. Clocks may continue their steady count, yet internal rhythms rely partly on changing light to regulate cycles of alertness and rest. When those cues vanish, hours can seem to stretch or contract, flowing without clear boundaries. Researchers studying individuals in controlled environments without natural illumination have observed that the body's internal clock may drift, settling into patterns slightly longer or shorter than a standard day. The experience often feels unhurried, as if moments loosen from their usual sequence. Silence and stillness deepen this effect. With few external signals to mark change, attention turns inward, noticing subtle sensations that might otherwise pass unnoticed. Breathing, heartbeat, and the faint movement of muscles become more distinct. Some people describe a sense of unease in such conditions, while others report a gentle calm that arises when distractions fade. Both responses reflect the flexibility of the human nervous system, which can interpret the same environment through different emotional tones depending on expectation and familiarity. Psychologists sometimes refer to this state as sensory reduction, a condition in which the brain receives minimal input from the outside world. Rather than shutting down, neural activity often continues in vivid ways, producing thoughts, memories, and images that drift across awareness. In moderate forms, this quieting of stimuli can feel restful, allowing attention to settle. In more prolonged isolation, however, the absence of reference points may blur distinctions between imagination and observation, illustrating how strongly perception depends on contrast and change. Far from the glow of sun or star, darkness extends without visible edge, offering no measure of scale. In that boundless obscurity, the mind encounters a space that seems to have no end, shaped not by distance alone, but by the way human senses evolved to understand the world. Seen from a global perspective, this region occupies only a small portion of a vast interconnected ocean, one chapter within a much larger atlas of underwater landscapes. Across the planet, deep basins and long trenches appear in many places, each formed by the slow architecture of shifting crust. In the Pacific, chasms descend even farther than those of the Western Atlantic, while along other margins, narrow trenches trace the edges of continents like seams in the planet's surface. These formations share common origins, shaped by the same tectonic forces that press, fold, and draw the seafloor downward over millions of years. When compared with these distant features, the depths here belong to a familiar family of geological structures rather than a singular anomaly. Similar slopes, ridges, and faulted valleys exist beneath waters off Asia, South America, and remote polar seas. Instruments lowered into those regions record conditions much like those measured elsewhere, pressure rising steadily, temperature falling gradually, currents moving in patterns guided by Earth's rotation and the contours of the basin. Nothing in these readings suggests a boundary where physical laws behave differently from the rest of the world's oceans. Mariners and pilots crossing this area travel routes long established by trade winds and navigation charts, paths also mirrored in many other heavily traveled corridors. Comparable traffic flows through straits, along continental margins, and across open water in every hemisphere. Records kept by shipping registries and aviation authorities show that incident rates align closely with global averages when adjusted for the number of vessels and aircraft passing through. From a statistical viewpoint, this stretch of ocean behaves much like others that carry similar volumes of movement. Yet, Geography does more than describe land and sea. It also shapes imagination. Certain places gather stories the way coastlines gather shells, each tale settling upon the last until a reputation forms. When a location becomes associated with mystery, the name itself can begin to suggest meaning beyond its physical boundaries. Maps mark coordinates and depths, but they also carry labels, and labels can influence how events are remembered and retold. A disappearance in an unnamed expanse may fade quietly into archives, while one linked to a familiar phrase may echo widely. This interplay between landscape and language is sometimes called narrative geography, the tendency for human perception to weave stories into specific settings. Once a region acquires such an identity, new events occurring there may be viewed through that lens, reinforcing the impression that the place itself holds unusual qualities. Over time, the idea can seem inseparable from the location, even when measurements and observations reveal ordinary conditions. Placed alongside the many other reaches of the global ocean, this area rests within a continuum rather than apart from it. Trenches, currents, storms, and depths follow patterns shared across the seas, each shaped by the same planetary processes. In that wider context, the waters here appear not as an exception, but as one expression of a vast and varied world. Legends drift across the surface of the sea, the way mist drifts across quiet water, forming shapes that seem solid until they thin and fade. Over time, certain places gather more of these stories than others, their names repeated in books, conversations, and charts until the sound alone suggests enigma. Yet beneath the language and memory that surround such regions, the ocean itself continues its patient rhythms, guided not by rumor, but by the steady laws that govern tides, currents, rock, and life. Below the surface narrative, the seafloor follows its own ancient design. Layers of sediment settle grain by grain, shaped by distant rivers and shifting slopes. Creatures move through darkness in patterns older than any charted route, their forms refined through countless generations of adaptation. Chemical exchanges unfold in silence, minerals dissolve and reform, and unseen communities transform drifting matter into nourishment. These processes do not hurry. They unfold with the same quiet persistence that shaped the earliest basins when continents first separated and water filled the widening space. Science listens carefully to these hidden movements. Instruments measure temperature, pressure, salinity, and motion, translating the language of the ocean into numbers that can be studied and compared. Each reading reveals another small detail, a fragment of understanding added to a growing mosaic. What emerges is not a tale of singular mystery confined to one location, but a portrait of a vast system whose complexity extends across the entire planet. Every trench, ridge, and plain participates in that system, connected through circulation that links distant waters into a continuous whole. Even with modern tools, much remains beyond direct observation. Large portions of the seabed have never been seen at close range, and countless species have yet to be described. Signals travel slowly through deep water, and exploration proceeds with deliberate care, charting new terrain piece by piece. The unknown is not an empty space, but a field of possibility, holding structures, organisms, and processes that await discovery. Knowledge expands gradually, shaped by patient inquiry rather than sudden revelation. Stories will always gather where horizon meets sky, carried by imagination as naturally as currents carry drifting forms. They belong to human experience, adding color and meaning to the vastness of open water. Yet beneath those narratives lies an ocean that does not depend on myth to remain remarkable. Its depth, diversity, and quiet activity provide their own enduring sense of wonder, one that grows clearer the more closely it is observed. Far below every tale told above it, the sea continues in stillness, holding its secrets without concealment or display, vast and unhurried, inviting understanding while never hurrying it.